Welcome to Lecture 7 and 8 of the series, which is in week 5 of Comp 19512, Introduction to Computer Systems, where we'll be looking at processor relations to the primary memory and the different types of primary memory. As before, we'll start with Q3s, and let's move on to the lecture as Q3. The first Q3 is name the main components of the little man. If you remember, visualize that walled room that I talked about in the lectures, and you should be able to remember some of them. There's about 7. I'll give you a minute to think about them. Well, here they are. We have the little man in the middle of the room, if you remember, and on the left hand side we had the in basket for putting in a sheet of paper and the out basket for moving a sheet of paper out. And then we had the calculator, where if you performed an in instruction it went from the in basket to the calculator. And the inverse for the calculator, when you performed an out instruction, the information piece of paper flowed from the calculator to the out basket. So the other entity in the walled room was the mailboxes, which store the program and data, and then the program counter that can index through the mailboxes, and the reset that resets the program counter to 0. So question 2 in Q3s, what instructions do the little man instructions opcode below implement? So we've got 4xx question mark for A and 6xx for B. I'll let you think about that for a minute or refer to your last week's notes. And the answer is opcode 4xx is a subtract operation, and opcode 6xx is an out operation. So the metadata that you should think about when you think about opcode 4 is a little man goes to a specific address given after 4, which is xx, and subtracts the data on the slip of paper in the mailbox from the calculator. So that value must already, the previous value must be placed in the calculator. That means there's an implicit first load the calculator and then perform the subtract. Then the next one, the output, is basically taking a piece of paper from the calculator with 3 digits on it to the out basket. Now the final one says write down the opcode, or the code, address, opcode and mnemonics, so the 3 different columns here, for the flowchart here. So we've got 2 instructions. One is input X and the other is store at mailbox address 88. I'll give you a minute to think about writing down 2 lines of instructions. And the answer for these is the first one will be placed in mailbox address 00, and the opcode for in is 500 and the mnemonic short form is in. And then for the next instruction will be placed in mailbox address 01, and as it's basically storing the information in the calculator to mailbox address 88, it will be the 3 digits here will be 288, and mnemonics or short form will be STA88. Right, let's move on with the lecture, and we'll be looking at memory. So we're going to start the first part of the lecture. So the learning outcomes for this half of the lecture are looking at certain parts of the processor, and that is the processor and its relation to memory, and particularly the primary memory. So what we should understand at the end of this lecture, because that's what the exam questions will interrogate in the learning outcomes, is how is this memory, and particularly the primary memory, organized? So we need to be able to understand and maybe think about how it's organized. So the second LO, or learning outcome, is thinking about byte addressable. So that's a funny term, isn't it, really? So what does this mean, this term byte addressable? So if I was you, if I was thinking about this, I'd break it down into 2 terms, byte meaning 8 and addressable. But we'll explain that in detail a bit later in the lecture. The next concept we're going to look at is this idea of how the processor is physically connected to the memory. And there's three different channels. There's the address, the data, and the control bus. So each one of these is a bus of different dimensions. Address will be defined by how many addresses it aligns to for a particular processor, and the data, well, if it's an 8-bit processor, that will be 8 bits. And the control lines, well, but there'll be few of those compared with these two, address and data, and we'll see those in the lecture. Now the important thing here is that you can relate the number of address lines, the size of the address bus, to the maximum memory size. So if you think about this, if you had one line going into a memory, that would enable you to address two different memory addresses. Now if you think about it, if you set that line to 0, that's one address, and if you set it to 1, that's another address. And we'll go into that in a bit more detail when we look at how we might calculate these, given the number of address lines, or the size of the address bus, how we can then directly calculate the maximum memory size that can physically address. Then we move on to timing diagrams. Now, maybe the important thing that's maybe not stressed enough in the previous lectures is that the processor runs a particular clock rate, and it's synchronous or runs in step with a clock. The other devices, and we're going to talk about the memory devices in a minute, like the RAM, the primary memory, do not run as fast. So we're going to see in the timing diagram that outside the processor, when we're connected via the buses, these primary memory may take more time to actually move information to and from the processor. We're going to see these different timings are related to cycles of a clock, and it might not take one cycle to read or write, it might take 3, say. So we'll look at reading and writing, and that means putting data on these buses and how long we have to give them to move the data from the processor to the primary memory, and the inverse for reading. So we're going to look at a simple timing diagram when the timing diagram infers a 2D XY plot where X may be time and Y, the height above it anyway, will mean a particular level, maybe 0 volts or 5 volts or high or low. And we'll look at that and comprehend this idea of aligning reading and writing to a diagram. So the next thing we're going to do is how we're going to look at modern processors and how they, if they're not addressing, as this one implies here, 8 bits, byte addressable, and they might address 16 or 32 in one go, how they would do that. And that's more than 1 byte of memory. And we'll look at how that's sequenced or actioned or functionally undertaken for a modern processor, and how and why we need to do that. So we're looking at understanding and explaining and relating information here and drawing diagrams, and then we're looking at why and how, and the information we're really talking about here, which is the content words are memory, timing diagrams, address bus, memory size, and then we've looked at the fact that there's 3 buses, address, data and control, and we've had this idea that a location in memory which is addressable might be a particular size, and this has defined it as byte size, 8 bits. And then we've seen particular content we're going to look at is the primary memory. Let's move on. So let's think about this. Well, this is one of the first ever memory chips in the world. It's this chip here, the Intel 1103, and you can look at more information here at the URL here. So that's basically, even though it was some time ago, what one of the first memory chips looked like. Maybe you should be aware that it's got a number of pins, and there's a number of pins here and exactly the same number on the other side. 2 of these will be connected to power and ground to actually power this chip. The others will be pins like an address bus, a data bus, and then some read-write lines, control lines, and maybe a line here that tells it it's this particular chip that we're addressing. So that was really Intel's first step into the DRAM market in the 1970s. Now modern day DRAMs look totally different to this. So this one here is Intel's SRAM. Okay, and you can see from here it's very, very symmetrical, and you might guess that there's buses going down here, and these are the actual storage locations here that I'm indicating with the arrow moving. So Intel's address RAM here is a static RAM, which is totally different to the dynamic. We'll have a quick look at that in the lectures and talk about it. So this is the latest technology really, which is 2007, which is quite a few years on 1970. And this is very leading edge sizing of these devices. So the reason I'm showing you here is to try and give you some insight before we move on to the theory, how these devices, well, they physically look different from the very first to the newest, one of the newest anyway. And then we look at a different type of memory, this one here, which is an EEPROM. So this is based on storage of data in capacitors, and you must keep refreshing it, this very first RAM, whereas this one is made up of about 5 different devices configured so they can store memory, and it's static, and that means it doesn't have to be refreshed like this dynamic one. And then this one can actually be reprogrammed. And the important thing about an EEPROM, electrically programmable read-only memory, is that it has this area here which you can basically change the information by excuse me, applying ultraviolet light through this window. Again, if we look at this, you'll see that here are the storage locations, here are the drivers for the pins, so you can see that the drivers are very big physically, and here are some buses and drivers for the memories around the side. So I thought I'd show you that just out of interest. Now let's start talking about the real point of memories. And the most important thing to remember, maybe if we first thought about this back in lecture 2, is that we're talking about storage of single instances of information. These are called bits, or binary digit. So we're going to talk about explicitly bits and bytes, and here we can see that we can store 2 different values in a bit. It can be set to a 1 or it can be set to a 0. So we talked about this in a previous lecture. We also said to get more information we need to cluster these bits together, maybe call that a collection of them, and then when we name these, the correct naming convention for these 8 bits, this is termed a byte. Now we're starting to see where this terminology byte addressable comes from. So let's try and imply what this means. It means that address for a particular memory addresses a byte of information. Okay, so the memory system are normally, and this is based on some of the very first memories that developed, byte addressable. Now let's look at this sentence at the bottom that tries to highlight this. And I'm going to read this out and then maybe explain this. That is, each unique address is capable of storing a byte. Open brackets, 8 bits, close brackets. So what it means is if you set up an address to a byte addressable memory, you will be addressing 8 bits at that location. So byte addressable means you're going to address 8 bits of information given a specific address. Now let's move on and try and have a look at this diagrammatically. So if this was byte addressable, each one of these locations might store 8 bits. But we can see here in this diagram we're depicting as having only 3 address lines. Okay, so with all these possible options and combinations, we can have 0 to 111 numbers of 8-bit locations. So we can have 0 to 7. So there's 8 locations we can address with a 3 bit address lines. So what we're looking at here is the memory capability given specific information. One, given an address line width of 3 bits, it will address only 8 different locations. Okay? So each of these bytes, if we put on an address bus 100, we'll specifically be addressing byte 4 in the 8-byte memory. Okay? So when we look at this analogously to our previous lecture, the LMC, Little Man Computer, we'll see this is like addressing the 00 to 99, the 100 mailboxes. Same sort of thing. We're putting out an address to find a location in memory. The only difference is the little man's computer stored 3 digits, whereas we may be storing 8 bits of information. So let's move on. So now we're going to look at a diagram that explains how the processor and the primary memory, RAM, are connected. So let's look at the different connections that make up this means of transporting data from the processor to the primary memory, writing, and from the primary memory back to the processor, reading. So what do we need? The first thing we need is to be able to transmit the data on, now here's a technical term, on a bidirectional bus. That means it can transmit data and write, and transmit data and read. It's a two-way channel. So that's one of the first buses we need, the data bus. We also need a location to place this data for writing or reading, so we need an address bus. But then we need some controlling mechanism. This controlling mechanism is done in this control line bus here. So these buses, this will be defining the size of the memory, the address bus. This might be, if it's an 8-bit processor, an 8-bit bus, and these might be maybe 3 lines, which are the control lines. So in a minute we're going to look at these buses and try and comprehend in a bit more detail what each one of them does and how the control lines are very important for controlling on the processor's behalf the flow of information to the memory, the primary memory. So now we're going to look at these. So what these are, the address, data, control, are actually used to be on printed circuit boards, wires. On silicon they're laid down as tracks, but they are still, a bus is a collection of wires. Okay? So these, for each processor to memory, in this type of configuration, require 3 different buses for selecting a particular location, the address bus, for moving the data in and out of the memory, the data bus, for telling the memory if you're reading or writing, the control bus. So let's look at these in a bit more detail. Remember, the processor really is the main guiding hand, it's in control. So the processor uses this address bus and writes to the address bus a specific address. The data will be stored in the primary memory, written to, or loaded from the primary memory, read from. Now the second bus is the data bus, and this will be the bus where we transfer to and from the explicit data. If you like, if we're looking back at the little man, it's the piece of paper flowing between the calculator and the in-basket, or the calculator and the mailboxes. So let's just explain what's happening here. What it will do once it's set up an address, because that's the first sequence of processes that has to happen, is after the address has been supplied, it will then load the data into the processor from the address bus, or write the data to the address bus, sorry, the data bus. Sorry, that previous one should be the data bus, does the transfer of data. So let's restart that then. The processor will read the data bus when it's loading information from the primary memory, and it will write to the data bus if it's storing data to the primary memory. Now finally, let's see what these control lines do, or control bus. What they're actually doing is saying when this is a valid address. So it'll tell the memory, it's time now to read the address bus. It'll also tell the memory if it's a reading and write, if you're putting data onto the data bus, or if you're reading it from, if you're the memory. So these control lines are used to tell really the memory to load the address and then to read or write onto the data bus the information. So let's go and look in a bit more visual way what a bus is. So this is being a bit silly really, it's not a double-decker London bus, red bus, but being a bit more detailed, it is actually something like this. It's a bit beyond the scope of the course to show you this, but it does show you the diagrams we're going to show you are relatively basic introductions. This is really what a memory does if it's a DRAM. What it actually does is it takes in the address, splits it into two separate addresses, splits it in half basically, and then it does a column address scan and a row address scan, and that's where we get the idea of CAS and RAS, and these are row address and column address, which gives you a particular memory location in the memory, and this is either read off or written into once this memory location has been set up. Now that's the technical detail, which is a bit beyond the scope of the course, but now let's look at a basic bus. So what we're talking about with this type of bus, be it this one or this one, is communicating information, which is a collection of wires will be given an address or used to transmit data. So each transfer, a single wire, transmits a bit of information, which on that wire can either be set to a high, a 1, or a low, 0. So let's look at this then. So therefore, with a particular size of bus, a bus width which we can define, we can have a number of distinct values. I did give you an example of this before. I said if you've got a 1 line or wire, that can address two locations, address 0 or address 1. Now, if you have, say, 8 lines, an 8-bit bus, 8 wires, the calculation for working out how many different values you can transmit on that is 2 to the number of bits you're transmitting on. So it's 2 to the power of 8, and that equals 256 different values which you can transmit across a bus of 8 bits. So we've already seen this type of calculation in the previous lecture, lecture 2. So this is a visual depiction of an 8-bit bus. When we're seeing we're going from A to B, maybe the processor to the primary memory, and each one of the bit lines or wires is given a particular naming convention. Bit 0, the least significant bit, and bit 7. And here we have a set of values that are placed on the lines, and if we're transmitting from A to B, this means that this address or 8-bit value will be placed on this side of the bus and it will be transmitted in this direction. Okay, so this value here that we've set up is equivalent, and that's in base 2 or radix 2, is equivalent to a decimal of 146 base 10. So there you can get the idea of placing information on these lines and then transmitting the information along from place A to place B. Okay, so you've got this idea of transmitting a bit pattern, 4 bits a nibble, 4 bits a nibble, 8 bits a byte. A byte of information along an 8-bit bus or across. Now let's move on then. So now we can see that what we're talking about here and the correct naming conventions for these information being placed on a bus is logic levels, or more precisely if we're talking about maybe electronic engineering and the devices, voltage levels. So what happens here is over time a voltage is placed on one end of the bus and then it is transmitted along the bus, so the bus magnitude of a particular wire, the logic level or the voltage level on a particular wire will change, go from 0 to 1. So that means the wires may over time change their levels or logic levels. So Let's add this to the note. So the thing that depicts this is a diagram. So like many diagrams, it's an XY graph where X, one axis along the bottom, is time, and the other axis, Y, gives you the idea of a logic level. And we'll look at this because the timing diagram itself is a bit more complex than that, but it gives you an idea of a timeline against a level and changes in these levels. So we're going to look at a relatively simple timing diagram, and this will be on the next slide, and we have a number of wires, and we're going to change the values on these wires from particular values to another value. So one of them will change from a low, a 0 to a 1, a low to a high, and the other will change from a high to a low. And it may change again afterwards. So let's look at these and say when they do change, the explicit region on the x-axis where they change from one level to another is called a transition. Let's go and look at these diagrams in detail then. So here's some timing diagrams. We're at the very start of two signals being transmitted. One of them initially is 0, one on line A is 0 at the low state, and on line B it's high or 1. And this line here gives us a timeline across the screen from left to right. Now let's see what happens in this timing diagram for these two signals as they vary over time. So one of them varies from low to high to low again. And these periods here are the transitions from low to high and from high to low. So these are transitions. Now let's look at the other line and see that this varies from high to low, and these two are the transitions from high to low. So over time we can see that these two lines vary, and it has a number of transitions where they change levels or voltages. So they change logic levels from 0 to 1 over specific intervals of time. So now we can see that maybe this is quite easy to see with two lines, but if we're starting to get to big processors with large memory addresses or large data buses, we might get to the sizing of number of wires collected together where we've got 64 wires, which is quite a large bus. And these are gathered together and could be seen in a single row on a timing diagram. So let's look at that when the buses themselves get larger. Now we're going to look at this timing and look at the transmission of data over a particular bus given a particular value or numeric value. And then we say when we're not really interested in particular areas, when we don't care about particular logic levels, we're going to say that we're going to cross-hatch that area. So we'll see this in the diagram on the next page. So let's just reiterate what this means again. I'm going to read out this sentence to make it a bit more explicit. Times when we do not care about the values, and that's the logic levels of the bus, comma, are marked by cross-hatching. So let's look at that in the next diagram. So now we've got a diagram that's going to be displayed in a minute. There's a number of areas in the diagram, and we've got a timeline along here again from left to right, and there's timing periods T1, T2 and T3 where we may be interested in the logic levels and how we might represent a number on a larger bus than we've looked at before. Remember previously we looked at a 2-bit bus, which isn't the norm. We're going to look at a 16-bit bus and see how we'd diagrammatically depict this. So let's think about 3 different periods, T1, 2 and 3, when the values might change, and other periods outside these, which we're going to see in a minute, which we don't care about. So if you remember, we called these areas and we depicted them by cross-hatching the areas. So let's look at this timing diagram for a 16-bit bus and how we might denote or add metadata to this diagram to state the values of this 16-bit bus at these different periods, T1, T2 and T3. Let's do that now. So the first thing to realise at this period here, before T1, we're not really interested in the values of the bus, which is a 16-bit bus. So we've cross-hatched the area. We don't really want to know. But as soon as we get from T1 to T2, the value we depict by these hex values. Remember hex, that's a nibble. So there's 4 nibbles there. So if you remember, hex just means that you've got 4 bits, and instead of going to a number of decimal characters, we use a single character to count all the way up 0 to F, which is 0 to 15. So if you remember, A is 10 and 0 is, well, it's obvious. So let's look at this again. So this is a 16-bit bus, that's 4 bits, 4 bits, that's 8 bits there, another 4 bits and 4 bits, that's 2 sets of 8 altogether, that's a 16-bit depiction, and this is the value from the period T1 to T2. Now remember, these are transition periods, when it transitions from its previous value to the next. And then the value changes at T2 to another value, 1F, 3F, where it previously was A0, A0. So the important things to note about this diagram, which we should comprehend and understand, is before T1 it's an unknown value, therefore the diagram is cross-hatched. After T1 and before, prior to T2, the value in hex, base 16 anyway, is A0, A0. Now if we look at that in base 2, we get these digit patterns, 1s and 0s. And this is between T1 and T2. Then if we look at the next value between T2 and T3, we see we have a different logic level. 1F, 3F is what it represents in hex, base 16, and this is the bit pattern, base 2. Then after T3 we see again, we don't really care what the value is, and it's cross-hatched. So now we're going to look at this value in a different diagram, again with 16 bits, D0 to D15, so we could say it's a data bus, and look at it in a different way. So this is this value here, changing to this value here. Okay, so that's one of the values, and we're seeing the transitions if they change. Now the important thing is, on buses when we're transmitting data, each bus could be in a 0 or 1 state. If we don't care what they're in, then maybe it's important to have a different state of bus, and this is that I'm going to read this out explicitly. Some systems are designed so that they, when there is no valid value or signal for the bus, it is set to a high impedance state. Now at first touch to these 3 words you might say, what does that mean? So let's break it down and drill down. Start with state. That is a bit like level. It says, is it a high or a low? And impedance is this idea of resistance to flow, because impedance is related to resistance. And high means, well, it's actually a very high value that doesn't take much current. Now one of the things that is a bit beyond the scope of the course, but the reason that buses are normally left when they're not used in a high impedance state is so they don't take current. So buses are normally left in and start in a high impedance state, and then they're driven to a low impedance state by putting a 1 or a 0 onto the bus. And what it actually means is high impedance state is no value. Okay? Now let's just read out why this is done and a rationale for this to be explicit for this course. And I'm going to read this paragraph here. The reason this is done is to allow many different devices to share the same bus, allowing one device to drive the bus at any time without interference from other devices, open brackets, which will put their buses into a high impedance state. Now what this actually means is, what I haven't told you is, normally on the buses there are many devices connected. So there might be one processor, but there might be 4 or 8 memory chips, but you're only addressing maybe a particular memory chip at one time. So all the others shouldn't be driving the bus, so they're set into a particular state, and that is a high impedance state. So this is the rationale here for high impedance state in this course. So now let's look at high impedance state and how we might depict it in our diagram we've seen before. So again, we've got T1, T2 and T3 for these periods. Now let's look at it here. So here we depict the high impedance state by a single line at the center line of this diagram, as opposed to crosshatch in the previous line. High impedance is a single line prior to T1 and post after T3. So this means the address or data bus is set to high impedance, so nothing's driving it and it won't take current. But the major implicit is one or other of the devices can drive it when it's set into this state. Okay, and you should be able to notice the difference between this and the previous slide where we had cross-hatching. Particularly the values are exactly the same, but the device driving depiction in the diagram is different. Now, actually every single operation in these processors is in lockstep. That means that you must align to a particular signal for everything you do when you're talking to the processor. The terminology for that is synchronous, and that means it must be timed relative to the clock. So there's a clock, and if you remember, I talked about that when I talked about the motherboard, and the processor is connected to a clock, and there will be a clock line coming to the processor which drives it at a particular frequency, and everything happens in lockstep with that clock. So let's read out this subparagraph here. This means that the operation in hardware are all timed relative to a clock. And the clock itself will be alternating from 0 to 1 and then back from 1 to 0 all the time. So this will be very regular and cyclic. So let's look at this in a diagrammatic view. So now we're going to look at a particular clock signal. We're going to highlight when it changes from a low to a high and call that particular naming convention, and also highlight when it goes from a high to a low and call that another naming convention. So here we can see this is a clock running all the time, and it has particular characteristics. This repetition from a low to a high to a low to a high, this is a period, and there's a particular relation in mathematics to this and the frequency, which we'll see in a minute. Now the other metadata we should be aware of is this edge here from a low to a high is called the rising edge. It rises from a low, rises to a high. Once we're at the high, we can fall down to a low, and that's called the falling edge. And particularly on measuring equipment, these are the naming conventions we'd use to look at that edge and that edge. And the important thing here is the clock itself repeats every t seconds, and it's cyclic. So the important equation that you need to know is you can work out, given this clock period, the frequency of the clock. And then if you know the frequency, it's 1 over f gives you the period. So f, the frequency of this signal, is 1 over t, the period. So f is frequency, and this is number of times it repeats each second, and is given as 1 over t. And this was giving a naming convention by the first person who developed an understanding of this, if you like, which is hertz. It's represented in cycles a second, a hertz. So, what if we have a period of 0.0001? Okay, what would this be given this formula? So given this period, that is 1 over 0.001, and that gives us 10,000 hertz, or 10, using SI units, kilohertz. 10,000 cycles a second. 10k cycles a second. So another clock frequency is maybe specific to a real-world application for a processor is 3.4 gigahertz, has a period of 1 over 3.4 times 10 to the 9, g, giga, is 10 to the power of 9, and this gives us a period of 0.294 times 10 to the minus 9. And minus 9, the power of minus 9, is nanoseconds. Okay, so this is 0.294 nanoseconds, or 294 picoseconds. So if you're not used to SI units, you can find them on the web, and you can see that there's a lot of values that are related to the power and a symbol that relates them. So micro is this symbol here, milli is m, 10 to the minus 3, and then if we get to memories you might be aware of, 10 to the 9 is capital G, giga, and we're starting to get to memories for hard disks anyway, which are T, which are tera, which is 10 to the 12. We're also interestingly getting to processing speeds in supercomputers of peta floating point operations a second, which is 10 to the 15. In the next few years we're going to move to this processing speed, ecta, which is E, which is pretty amazing. It's 10 to the 18 operations a second. So here we can see the scale from large amounts to very small amounts. Okay, so we're going to stick to the SI prefix when we talk about time or size. So these are SI units, and you can find them on a particular website. If you look in Google and just type in International System of Units, it will find the actual website. So we should know about SI units now. Now we're going to look at a particular timing diagram. Now I should explain that we've got some insight now into what timing diagrams are. First, everything that happens with respect to the buses and either reading or writing information from the processor to the memory is done in lockstep with the system clock, normally on the rising edge. The important thing to realize is the processor and its internal registers may be able to process information very quickly internally in one cycle, but normally outside the processor on the system bus and the memory will be running at a slower rate. Therefore it will take a number of clock cycles to process data. So therefore, let's start at the very top here with T1, T2 and T3. So it nominally takes, in the examples we're going to show, 3 clock cycles to perform a memory read. Now let's start going through and adding the other buses to this. So this is telling you that everything that happens below is in lockstep, synchronous with this clock, which we're going to see in a minute. And what's going to happen here in each one of these periods, in period T1, this one, we're going to generate a memory address, and then we're going to enable it and tell the memory that that's a valid address. So that's really 2 steps. Then T2, we're going to use that and generate a memory once it's decoded with a specific address we've got in the first period, and that will give us and generate a memory location. Then in the final period here we're going to see that we actually, if we're doing a memory read, we read back the data from the memory back to the processor. So it takes 3 cycles. Now let's go through them one at a time. First, here it highlights every single signal we're going to see below is synchronized to the clock. Let's look at the first signal. So the first signal then is where in T1 the processor places on the address bus a valid address, but the memory doesn't know yet. So that's the first step of operation to undertaking a memory read. The next, 2 things happen. First, the processor enables a control line And the control line is an enable to say this is a valid address. So it's an address enable control line. And it tells the memory in the second half of the first cycle that the address on the address bus, so you can see it's taken half a cycle to set up the address, and then the memory can read it, and it's told at this second half of the first cycle T1 that it is a valid address, and it's told that by the address enable line going from low to high. So now the memory knows that it can lock that address into its memory and generate that data. So this data, once it takes T2 to actually obtain that data, and at T3 we will see that the data on the data buses, because this is on the address bus, is now valid and ready to be read by the processor. And the processor will signal the memory to tell it if it's putting data into it or taking data out of it. Putting data in is storing, taking data out is reading. So it gives it another signal on another control line. One control line we've already activated and then deactivated in this period. Another control line is the memory read that tells it we're going to read data from the memory. So it tells it this is the address. Now it's a valid address. You use it to go and look up the actual location in this period here, and then it tells it in T2 if it's going to read or write, and it's going to tell it here by the memory read line going active high that it's actually going to read the data from the memory. And in the third phase here it actually reads the data because the system knows that in the third cycle T1, T2, T3 the data is actually valid. So it takes 3 cycles to read from memory. So that's implicitly telling you that the memory is slower than the processor. Let's move on. Now we're going to look at writing. So this is nearly exactly the same. We're going to stress again the 3 periods where we're going to set up an address, then we're going to enable it in a particular time slot, then we're going to tell the memory if we're which way we're transferring the data, in fact, which is writing the data, and then we wait until the final period here when we actually write the data to memory. So let's go over these timings. So again, every single phase is synchronous with a clock and in lockstep. So let's look at the first signal then. First, the processor puts out an address, which is a valid address on the address bus. Then in the second half of the first cycle T1, it tells the memory this is address enable line going high is a valid address, so lock it into your input addresses and find that location. And then the memory will find that location. As yet we haven't signaled it to say which way we're reading or writing, so finally another control line. These are the control lines, the address enable and the memory. This is the memory write. So the memory write control line goes high and tells the memory that we're going to put data on the data bus, and the processor is going to put it on the data bus, and then the memory will read it because we're writing into the memory. Okay, so now you can see that every phase here is in lockstep with the clock. In the first period we put an address out, and then the second half of that we tell the memory at the other end of the address bus that it's a valid address. The memory takes that address and finds the actual data, or maybe where it's going to store the data, and then the processor again with a control line in the second and third periods tells it that actually I'm going to put the data on my data bus and you're going to read it from the data bus because we're writing to memory. Okay, so that should give you the sequence of operations, 3 cycles to undertake a write sequence. So again, we're just quickly highlighting that that was a read. The only difference here again is that the memory read line goes high for a read, and for a memory write, the memory write line goes high. So the big differentiator is which one of the memory read or write lines goes high, tells you if you're writing, or let's just go back, reading. Let's move on then. So now we see that the address bus widths, as we've talked about before, is defined by a number of wires. And what this governs is a particular number of unique memory locations. And what we can do by knowing the number of wires, or the width, is work out the maximum, or actually the naming convention we must align to is the address space, explicitly the address space size. So let's look at that. So if we've got a space of 2 to the n, where n is the number of wires, and that will give us the address bus width, so n gives us the number of lines in the bus, particularly in this case an address bus. So let's look at some examples of this. If we've got a 4-bit bus, that's 2 to the 4, that's 16 different locations we can address. Different locations. If we've got a 10-bit bus, that's 2 to the power of 10, that's 1024, which is in SI terms 1 kilobyte. And if we've got 32-bit, which we have had 32-bit machines for address buses, that's 2 to the 32, which is a 4 gig addressable address space. Okay, so the important equation to remember when we're talking about calculate the address bus size, or address space size, or maximum, is we take 2 to the n, where n is the number of wires or the address bus width, and that's 2 to the power of n, gives us the size of the address space, or the maximum size of the address space. And again, these are in SI units. So we'll take a break now and stop for a break. So we're back after the break, so let's move on. So again, just a quick reminder of SI units and the fact that if you've got a power of 2, you can work out some maybe important information, like a 32-bit address bus gives you 4 gig of space. So let's move on from there, and what we're going to talk about now in relation to address bus is the size of the memory. We can determine this or calculate this from the number of address lines. So let's do that then. If you add this blank here, so that is that n equals log to the base 2 of the address space. Let's give you some examples and explain what this equation does and is. So if we have 512 bytes, how many address lines do we need to address that size of memory? So we take log to the base 2 of it, brackets 52, and we find out what this power is of power of 2, and we find if we take 2 to the 9, that will give us our number 512. So therefore, using this equation, a simple way of doing it is to say, look at the power, and it's 9 lines. So let's do this with another number. So we're going to look at a 16K, 16,000 byte memory. So this is, again, log to the base 2 of 16K, which is 2 to the 14, which gives us 14 address lines, or the number of address lines for a 16K memory is 14 lines. So let's look at another example. So if we've got 16 million bytes, then that's log to the base 2 subscript 2, 2 to the 24 gives us 16 megs, and that means if we take this power, it has 16 meg has 24 lines to address that number of different memory locations. So if we look at a table of all the possible different powers, we'll see that ours here, if we've got 9 lines, that can address 512 memory locations. If we've got 14, that can address 16,000, really it's 16 8,384, then if we've got 24 lines, that will address 16 million. And that's here. Okay? So that's where these powers relate to. And if you want, you can move up the scale just by timesing by 2 all the time. Okay? To get this one given 0 upwards for the powers of 2. So, if you want to know what a logarithm is, because if we look back, and here, this term here is a logarithm. So, previously people have asked, what is a logarithm? Well, I've given you a lot of URLs where you can go and see what it means, and it will introduce itself in these resources. So I'll let you go and interrogate those yourselves. And these are learning resources. So now let's go back to this term byte addressable with relation to a data bus. So a byte is 8 bits, and each 8 bits has a unique address. So that means when you read a byte, you get 8 bits of data given this unique address that locates it in a particular position in memory. So byte addressable means you will address a location in memory which stores 8 bits of data, and that's with relation to a data bus. So now what we're going to look at is the fact that depending on accessing of memory, you can see that a processor has different times involved with processing data, and the processor will be running at the clock rate, and that will be interchanging information only between its internal registers. When you move outside the processor via the address bus and then connect to the memories, these are running at a slower rate, which we've already implicitly seen, because when we've been undertaking memory reads and writes, they've been taking 3 processor clock cycles. So the memory in a system is slower than the processor. So most operations or operands, be they integers, which are 1, 2, 3, or floats, which is 1.7, or doubles, which are more accurate floating points, really have to be accessed not by 1 byte, 8 bits, but maybe to get larger numbers, this may take 4 or 8 bytes to access a larger amount of information. Say an integer will be mapped to 4 different locations, each one containing 8 bits. So what does this mean then when we're reading information from a memory? When we have to do this, read the data from memory, and if a number, an integer, is placed in 4 different locations, what does this mean? Let's go and have a look at our next slide. So the next slide will give us a view of how we do this when we're fetching the information, and we're not fetching a single location of 8 bytes. We have to fetch maybe 4 different bytes to make up the whole number. So what does this look like? Remember, we're thinking about here fetching sequentially a number of bytes, 1 byte each time. Let's go and look at this then. So if we look at a data bus that's wider than 8 bits, 1 byte, how would we transfer the data? So this is actually the case for modern processors, when typically they'll have data stored as 4 bytes or 8 bytes, so a 32-bit number or a 64-bit number. So we have to think about transmitting 4 separate bits of information, separate blocks. So let's look at this then. So the question here is then, how do we do this? How do we read in 32-bit bits at a time? How do we do this when our memory is set up to be byte addressable? So we put out an address, and that will only address 8 bits, and there's 4 of those in the 32-bit number. Let's go and have a look. Well, this diagram tries to depict it. So the diagram itself is visualizing reading and writing multiple bits. The data bus might be 32 bits, and the address bus could be 32 bits. But the address bus might only address a particular location. Not all 4 you require for 32 bits. So 32 bits is, let's just step through each number, and this means that each one of these digits is 4 bits, the next one is another 4 bits, then another, then another. So let's add them up. 4 bits for the least significant digit, the next digit on is 8 bits for those two combined, the next one on is another 4 bits, that's 12, and the next one, no, that's not quite right, that's 8, 16 and 32. So we're moving on to 32-bit word address here. Okay, so if we put out a word address, this only addresses one of the locations in a 64 kilobyte memory. So with this number of bits, we've only got 64 of these locations we can access, which goes from 0 to all F's. And the important thing to think about is this assumes a 16-bit address bus. Okay, so let's just check this then. That's 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it should be a 16-bit word there. So that's actually an error. It's a 16-bit address bus, not 32. So what does this mean? Well, it means you're outputting 4 nibbles or 16-bit address into a memory, and with 16 bits this is only addressing 64 kilobytes of memory, but what we want to do is feed in a 32-bit number. So we're going to have to break in reading or writing those into 4 separate reads or writes. Okay, so the important thing for you to comprehend here is reading and writing multiple bytes given a 16-bit address bus with a minimum address of all zeros, this one, and a maximum address of all F's, means we've got all these locations. But actually we don't want to read an 8-bit or byte addressable memory, this one. We want to read a 32-bit number, which is 4 bytes. So we want to read all of these at one time. So let's look at that then. So the system is organized so each byte is multiple bytes of data. So 32 bits is 4 8-bit bytes, and this maps onto a subset of address memory. So let's just go and look at that. What does this mean? It means if we're reading this address and this number, which has a 32-bit number, we have to access addresses all zeros, 1, 2 and 3 to access the whole 32-bit number. Now let's move on. So this means that we're talking about word addressable memory. So let's go back and look at that then. So this is a 32-bit word, 8 bits, 16 and 32. 32-bit word memory. Okay, so now the naming convention we're going to use is word addressable as opposed to byte, where word has to be specified in size. This is a 32-bit word addressable memory, and it's a set of 4 bytes corresponding to 4 different addresses. So each of the 4 different addresses, the 4 bytes, has a separate or unique address. Let's go and look at that. So for the first address here, the address is to get the first 32-bit word, we need to address different locations, 0, 1, 2 and 3. So let's have an example of this to make it even more explicit. So if we're reading or writing multiple bytes, say if the processor is reading from word address 0, and we've looked at that previously on the slide. We have to read addresses 0, 1, 2 and 3, and that's for a 32-bit word. Similarly, if we're addressing this address, FFF8, we have to address these different locations: FFF8, FFF9, FFA and FFB. So to get a 32-bit word, we're actually outputting 4 different addresses, and the base address for each one of these is 0, and for this one, FF8 is the least significant byte address. And this is called word addressing via a byte addressable memory. So again, have a think about rescan reading these lecture notes when you're revising, and the next thing to look at is we're going to look at primary memories. So let's look at the next section of information and look at their learning outcomes. So we're going to look at some issues here. The learning outcomes from this part of the lecture is the primary types of memory. We need to be able to explain the difference between 2 naming conventions, and these are quite important. One of the naming conventions for a particular type of memory is volatile, and the other is non-volatile. So we're going to explain the difference. Once we've done that, you'll be able to explain the differences between these 2 types of memory. The next thing we're going to do is give you a view of the basic characteristics of different types of primary memory. And these are particular naming conventions: read-only memory, random access memory, static random access memory, and dynamic random access memory. Short forms for those are ROM, RAM, SRAM and DRAM. So we can look at these naming conventions and try and give you some insight into what they actually are. Then we're going to look at this idea of dealing with this problem we've just looked at dealing at memory that's more than a byte. So 32-bit data is 4 bytes. How do we deal with that? And we deal with that, and manufacturers used burst modes to deal with larger blocks of information. So we'll talk about what this means in a minute. Then we talk about synchronous RAMs and explain what this means, the naming convention. So we're looking at quite a bit of new introductions to naming conventions, explaining the theory behind them and the basic characteristics of different types, and then a particular type at the end which is called a synchronous RAM. So the first thing we're going to say is these are covered in a number of resources, particularly in the library, which are books, one is Tannenbaum's Structured Computer Organization. There's probably a newer edition than this, and the other is Computer Systems: A Programmer's Perspective, also covers some of this material. So primary memory's characteristics. Well, the first thing to realize about a memory is that you can put information into it and take information out. A naming convention for this is reading from or writing to. So the processor itself must be able to undertake these type of instructions to read information and data from the memory and be able to write as well. Now, the important issue for different types of memory is some of these, when the power goes off, lose all the information. So what happens when the power goes off? What are the names of the memory? And we've got naming conventions for this. So one of the things we're going to see in a minute is which types of memory keep the information when the power is removed and which types don't, and we'll see the naming conventions in a minute. Then we'll also see which ones are cheaper, and you might have guessed that the faster the memory, the more expensive it is. So that means that the speed is related to cost, and it's also related to size. And also, as we move away from the processor towards the hard disk, the time it takes reduces. Well, actually it increases because they're running at a slower clock speed, and we've seen that already implicitly when we're reading and writing data to primary memory, it took 3 processor clock cycles to read or write data, whereas internal processor register transfer will be done in 1 cycle. So that as the processing of data moves from the processor to the primary memory to the secondary memory, primary memory is normally RAM and secondary memory is hard disk, we'll see that the time it takes will be longer. So let's look at this idea of naming conventions then. So the first naming convention is when we take the power off, we lose the information. The naming convention given to the memory then is volatile. So particular memories, when we remove the power supply to them, everything's lost, and they're called volatile memories. Now non-volatile memories keep that information even when the power's removed. And we'll see what they are in a minute, the naming conventions for these different naming conventions align to particular types of memory. So a computer system does need some amount of memory that is non-volatile. Now this is a bit beyond the scope of the course, but the name for one of the parts of memory in a computer, like a personal computer, is a BIOS. That is in, when it's started up, in this type of memory non-volatile. Okay? So in a particular end-user computer, when we load the program to run it, it's in this non-volatile memory. And this non-volatile memory will store the program and data which maybe loads the operating system. So it's embedded in this non-volatile memory and it's not lost. And we'll align non-volatile to a particular type of memory in a minute. So non-volatile memories are read-only memories. So a ROM is a non-volatile memory. And there's a standard ROM, which is manufacturers, and the important thing to realize is you can't change it, you can only read from this memory. And these are devices which, even though it's beyond the scope of the course, you program into them the BIOS, the basic input-output memory system for a PC, which will then load the operating system. You can only read from them. The manufacturer will program them, and they will be in the end-user computer embedded in it. So now let's look at different types of ROM, and there are many different types of ROM. The first is a PROM, Programmable Read-Only Memory. And this and these are relatively cheap. They're only used when a design cycle for a computer has been developed and designed and the design cycle is finished, because they're very cheap and they can't be reprogrammed. So a PROM can only be programmed once, and that's quite important. So you normally do it after you've built and tested the system. But while you're building and testing the system, you use EPROMs, erasable programmable read-only memories. And these can be programmed and reprogrammed a number of times. The way they're reprogrammed and set all down to normally a particular value is you expose them to ultraviolet light for about 15 minutes, and then you can reprogram again once they've been irradiated with ultraviolet light. And these will be used in the development phase of a computer, an embedded system. And these devices, the EPROMs, can be reprogrammed, whereas PROMs are one programmable and they're not reprogrammable. So these are used by developers, these are used by the end system builders, which build them at a particular price. So EEPROMs, which are electrically erasable programmable read-only memories, these are different to the UV erasable. These can be erased by a particular voltage line, an extra pin on these devices. They're a bit more expensive than the UV type, which we've just talked about here, which are EPROMs. So the EEPROMs can have their signal change, which may be important again and again, but with an electric signal as opposed to irradiating with the UV light. They can be reprogrammed a number of times, maybe not as many times as you can write to certain memories. They're pretty slow to program though, and they're more expensive, and they're not as dense as other memories. Okay, so you need, per bit, there's extra functionality around this storage functionality that requires them and enables them to be reprogrammed electrically. But that costs money and it's relatively slow to do that, and that means the density of the storage is less dense. So we've got three different types of storage. We have the PROM, once programmable, the EEPROM, ultraviolet erasable, and we have the electrically erasable EEPROMs. These are used a lot in systems that you've probably got, your phone and your camera you've probably used them without even thinking about them. So another type of memory that you've probably heard of is a flash, and this is a recent type of EEPROM. So a flash memory is an electrically erasable memory, and these are built into a number of locations. They can be in your camera, and they have about 100,000 erasures before you can't reprogram them again. So they do have a lifetime. And they're widely used in a lot of embedded systems, digital cameras and key fobs. But they tend to be much slower than other non-volatile memories. PROMs are cheaper. So flash are maybe more flexible, but maybe more expensive. Now we're going to look at the other type of memories and align it to a particular keyword. So RAMs are volatile. So let's think about this then. So the important thing to realize here is that a RAM, random access memory, is really the title given to the ability to put out random addresses, because you can randomly access different memory locations. Okay? But when the power is taken off a RAM, as we can see here, the data's lost when the power's removed. Now we're going to talk about two particular types, and this is where the term naming convention S and D comes in. Static RAM is one type, and they're constructed differently, and a DRAM. So let's go and look at these. Remember, both RAMs and RAMs themselves are volatile. So let's look at static RAMs first. They're very fast, they're relatively expensive, they take a lot of silicon chip area, they're bulky, and they're smaller size-wise than DRAM. They're generally used, as they're fast, as caches. So let's state what a cache is. So I'll say what a cache is. Cache memory is small, fast memory, generally static RAM. This is placed between the memory and the processor. So if we've talked about hierarchies, which we will do again maybe, we've got the processor, then the primary memory. Well, a cache is put between the processor and the primary memory because it's faster than the primary memory. So static RAMs are fast, expensive, bulky, but not as small as size in the amount of memory they can store, as opposed to the next type of RAM, which is DRAM. Static RAMs are fast because of the way they're made and their functional complexity. They take up more silicon area. Now that moves us on to DRAMs. DRAMs are really just capacitors. The strange thing about DRAMs as opposed to static RAMs is DRAMs, you have to keep scanning them all the time to recharge the capacitors. So they're refreshed. There's a hidden refresh cycle underneath using the primary memory as DRAMs all the time, because the capacitors will always be losing charge. So let's go over these notes and explain what a DRAM is. They can be very large memories, so they can be bulky memory stores, 4 gigs, 2 gigs. They tend to be slower than SRAMs. Okay, so an SRAM is more expensive and faster, but you can't have as much main memory. It will be smaller in size of the, size of area, and that means that they will be denser. So DRAMs do need refreshing on a regular basis. That's because they're really capacitors, and that means the charge they store for a 1 leaks away over time. So consequently we need to rewrite this data back to save it, and that's why when the DRAMs have power removed, they lose their information because the charge in the devices leaks away. So these are very low cost but extremely high density, and these are normally your DRAMs or the RAMs for your primary memory. They're relatively cheap. A number of varieties that have been made to go faster, and that's SDRAMs and DDRAMs. So how do they do this? Let's look at variants of DRAMs in a minute. So the first thing we're going to look at again is speeding memory access. Remember, we've already talked about this, and we're going to look at it in a different way this time because we're going to have to read memory. So let's look at speeding up reading slower memory. How would we do it? So if you remember in The Little Man where we went through a cycle of fetch, decode and execute, that's exactly what we've got to do basically in these memories. There are slightly different naming conventions for doing that though. Now the first thing to realize is this memory access is relatively slow. But there are a number of ways of dealing with this, some of which we'll meet later. So we can speed up the processor access times. And one technique to optimize this is blocks of data transfer. So instead of reading a byte, we read a block. So let's go and see how this might be done. So how would we access this memory to decode a block of memory? So we're going to read and write a specific address, and what we're really concerned is a significant part of the time is dealt with decoding and finding the address in the memory. So it's decoding that address at the chip side, the memory. So what we've got to do is find the right memory location to read or write to, and this takes time. So what we're actually doing here diagrammatically, a bit beyond the scope of the course, but you can see what takes time. First we take the address, and then we separate into two separate addresses, the column address and the row address, and we clamp that to drivers which will actually generate address and then find a particular data item and place it in the output data to be read or written to. So this process of setting up the address and finding that location takes time. But one method for speeding this up is to read an address word that follows. So wait a sec, what does this mean then? I'm going to read this out. One method that can be used to speed up transfer, that once the address has been decoded, so maybe we've got the address here, and we could just read off that address, that one, and that one, and that will give us a 32-bit word when each one is 8 bits. So that's interesting. Let's reread this again. One method that can be used to speed up transfer, that once the address has been decoded, to transfer not only the data in the addressed word, this one, but the data in the words that follow. So this one, this one, this one, and this one. So the address is nearby. So we've already hinted at this in the previous conversations we've had about this. So if we're talking about a 32-bit address, this address here might be this zero's address here, but we can also then address 1, 2, 3, and the other addresses next to them, which in this case might be this address for a block of 32 bits, and the next block will be 4, and the next block will be 8. Remember, we're addressing 32-bit data words here. Okay, so 0, 4, and so on. So let's have a look how we do this, and then we can do this every clock cycle as opposed to waiting for 3 cycles. So the hint here is, remember last time we were thinking about reading and writing data. It took 3 clock cycles per 8 bits. We could speed that up. Let's see how it's done. So this is done with synchronous DRAMs by decoding the first address, the base address, 1.5 clock cycles, and then reading subsequent addresses every half clock cycle. So we can read more data by decoding to one address, and then the addresses next to it we can read much faster. So this is specified for this column address strobe, and as we've just seen, we talked about that in our diagram we've previously seen, where we're going to find the column address and then the row address. And we've seen that this would be specified as a column address strobed. So the address setting up, we strobe it into memory, and it's called a latency of 2. So that means, where does this 2 come from? 1.5 clock cycles for setting up the first address, and then half clock cycle later for each subsequent byte. So it's a latency for a column address of 2. So with SDRAMs, they're usually organized, which is synchronous DRAMs, to transfer 64 bits of data. So each transfer of data is 8 bytes. Okay, there's 8-bit words in 64-bit data. So let's have a look at this then. So the diagram's going to show us transferring a number of bytes. So we first have to take 1.5 clock cycles to start the first address, and then subsequent addresses are done every half clock cycle. So let's see what happens. We've seen this sort of thing before, but for 8 bits. Now we're going to take a block of data. Okay, let's look at this. So first we set up, and we're going to show you what we're doing here, looking at this location first, and then the ones next to it. So first we set up the address, and then we enable that address, and then 1.5 clock cycles later we can actually read the first set of data after that. So then, once we've set up this valid address, we can read the data sequentially after that. Okay, so what we're actually saying is SRAMs enable you to read bigger blocks of data by setting up an initial data block address and then reading the addresses next to it. Okay, so that's what's happening. In this example, we've got a number of blocks of data being read, and after the arrival of the first 2.5 clock cycles, we can read out the valid data in 1, 2, 3, 4 periods, or 1, 2, 3, 4, 5, 6, 7, 8 half clock cycles to read out 64 bits. So actually it's reading out 1, 2, 3, 4, 5, 6, 7, 8 different bytes given a base address, which will be here, and then it'll read out subsequently after 2.5 clock cycles. Okay, so let's look at revising what we've talked about and looking at some mind maps. So the first thing to realize if we're looking at memories is that memories themselves are really talking about storing data. So the data is in a particular location given by an address, and that address will address the data item itself. So now let's start where we started previously and say the CPU or the processor is linked to the memory. It's linked to the memory by buses, and there's actually 3. We output an address, which then finds a data item at that address location, and then the control lines tell us in this interaction between the CPU and memory if we're reading and writing the data to the CPU or from the CPU. And then if we look at bus activity, we saw that if we were writing or reading data nominally to primary memory, it took 3 clock cycles, and we had to remember there was a number of steps we had to take. First, the processor outputs the address on the address bus. Then the processor activates or enables a particular address line that tells the memory that that's a valid address, and that address line is the address enable line, and it goes high. Then the processor needs to tell the memory if it's either reading or writing to or from the memory, and then the third period it will actually read the valid data or write it. Okay, so that's reading and writing, take 3 clock cycles and at least 4 different steps to undertake that. Now let's talk about sizes of memory. Maybe the first thing to realize is address bus sizes vary, and they can vary to be gigs or kilobytes, gigabytes or kilobytes, and we've got to realize there's different equations relating to the size of the address bus, particular size of memory, and this x will give us the number of lines given that size of memory. So for a particular memory, we take log to the base 2 subscript 2 open brackets m close brackets, and this m is equivalent to 2 to the power of x, and then x is the number of lines which will address that memory size. So the next thing we can look at is the bus width is n bits. We can address an address bus size, address space of 2 to the n. Okay, and then we saw how synchronous RAMs can be used to read a number of bytes sequentially given a particular start address or base address, and then we clock them out every half clock cycle. And this was our diagram we used to depict reading and writing into a actual memory, a bit beyond the course, but you can see now why we've got CAS. Column address strobe will be this one, and that will be row address RAS. So now we talked about a bit later on in the lecture this idea of keeping data and losing it. Keeping data means if the power is removed we still have the data. Losing it means if the power is removed we lose it. So we saw that volatile memories align to RAMs, random access memory. Then we had particular types. Static RAM, quite expensive and fast. Then we had two different types of these other RAMs, which was DRAMs, dynamic and static, or synchronous DRAMs, which are the ones that can basically read in blocks of data faster than, if you like, plain simple RAMs. Then we looked at non-volatile memories, and these are called ROMs, read-only memories, and we saw there was at least three different types: programmable, once programmable PROMs, electrically erasable EEPROMs, and UV erasable EPROMs. And then flashes are actually EPROMs. Now if you look at these, any questions you need at the end of the lectures, do ask me next week. Next week's Q3s are here, so you can actually have a look at them. So if I leave you now, this is the end of the lecture, and I will see you next week in the lecture series, and this is the end of the video for this lecture.